I'm very delighted to have you for this other episode of More Concept. I know you have inserted in another DVD, and that is very, very marvelous. We are continuing with our calculations involving empirical formula and molecular formula. For those who are watching me live, I thank you very, very much. My students in class, don't mind about the language of DVD. There are some people who are watching me as a recorded teacher. So Teacher's Light is still your teacher. Tonight, we are progressing with our moral concept. So this is how far we have reached. We are on a compound, that is example 4. We can read through. A compound contains 53.3% oxygen, 6.7% hydrogen, and 40% carbon. Okay, find the simplest formula of the compound. Hope now this is the simplest of all the examples we have so far encountered. So the solution is a simple one. What are we going to do is to first present the elements which are present in this compound. So elements present. Okay, so which elements are present? They have been given by the examiner. Okay, I can start with carbon, hydrogen, and then oxygen in that reverse way. Or you can start with oxygen, hydrogen, and carbon. Anything. We would like to start with that. Okay. So percentage composition is given. So I'll talk about it. Percentage composition. So is this percentage composition by mass? We don't know. We have just been given percentage composition. But hopefully it is by mass. So percentage composition, carbon, read well. 40% carbon, so 40%. Okay. Then we can talk about hydrogen, 6.7 hydrogen, and then oxygen is 53.3. Very interesting. Then what is next are the number of moles. So number of moles. So we are going to get our percentage. Hopefully it is by mass. We divide through by the relative atomic mass or the atomic mass. So atomic mass for carbon, assuming the examiner gave it to you here as 12, hydrogen as 1, and then oxygen as 16. Very interesting. So we divide through by 12, then the 6.7 by 1, the 53.3, then by 16. So the next thing is to get what we call the molar ratio. So molar ratio is going to be obtained by first dividing. So 40 divided through by 12 to obtain the mole here. I'm getting a 3.3. So I'll put it to 1 decimal point. Then this is a 6.7. So since it is ratio, then I'm going to put those two dots. Okay, then I'll go to 53.3, then divide it through by 16, which is also a 3.3. So we shall divide it through by the smallest ratio to get what we call a simplest ratio. So simplest ratio is going to be 3.3 over 3.3, which is the smallest, then to 6.7 over 3.3, then to 3.3 over 3.3. You will accept that this is already 1. So 1, 2, a 6.7 divided by 3.3. What does it give you? I'm getting a 2. Okay, so this is a 2. Then 3.3 divided by 3.3, that is already a 1. So we can go and talk about the empirical formula or the simplest formula. So we can come and say that therefore simplest formula. Did you talk about simplest formula? Yes, simplest formula is a CH2O. Very interesting. Hydrogen is 2, carbon is 1, oxygen is 1. So those are the number of molecules of the different atoms. How many atoms are contained in this whole compound? But these are not the actual. The actual ones can be got by the molecular formula. So copy this and then we look at example 5. Dear viewers, we'll be back from the break. This teacher slide. Okay, with the chemistry of tonight. So I'm reading through example 5. The examiner is saying a hydrocarbon. Oh, the language has changed. A hydrocarbon Z of molecular mass 56 consists of 85.7% of carbon by mass. Oh, part A, define the term hydrocarbon. Part B, calculate the empirical formula of Z. Part D, determine the molecular formula of Z. Very interesting, a very, very simple question which we can approach. Okay. Now, in this kind of arrangement, we can define a hydrocarbon. What is a hydrocarbon? Or what is a hydrocarbon? We are going to discover that as the word sounds, hydrocarbon, from hydrogen and carbon. So we are going to see that a hydrocarbon is a substance that consists of hydrogen and carbon only as its elements. We can write that as our solution for part A. So a hydrocarbon is a substance that consists of carbon and hydrogen only as its elements. So, in the topic of organic chemistry, we shall talk about a number of these hydrocarbons in different categories. Okay, in what we call homologous series. We shall talk about what we call the alkanes, the alkenes, the alkynes, the alkanols, which are called alcohol. So when you go with the chemistry, we shall talk about many, the esters, many, they are very, very many. Yeah? So at this level, you should be knowing all the definition of a hydrocarbon. But we shall talk about it in details. How people are benefited from that tonight. Then let us move to part B. We are supposed to calculate the empirical formula of Z. So part B, Mr. Examiner, sir, we know very well that in any calculation of empirical formula, we start with the elements present. After knowing that a hydrocarbon consists of two elements, we can state them. So elements present in this compound, elements present are going to be carbon and hydrogen. Write the correct symbols of those particular elements. Then we need to talk about the percentage composition, and this is percentage composition by mass. So percentage composition by mass. Percentage composition, yes, by mass. So we've been given the percentage, we have been given the molar mass, but molar mass for calculating the molecular formula. But we have 85.7 of carbon, so the percentage for carbon is 85.7. So the remainder now becomes for hydrogen. So we are going to get 100 minus 85.7. What do you get? Exactly 14.3. 14.3 is for hydrogen. That is in percentage. Then we need the number of moles. Number of moles. So the number of moles, we shall go and divide the mass, the percentage composition by mass, over the relative atomic masses. We know very well that carbon is 12, okay? And then hydrogen is 1. Good. So this will give you now a ratio, molar ratio, after dividing. Molar ratio. So the molar ratio, divide very well to obtain the number of moles and express them in ratio form. So 85.7 divided through by 12. I'm getting a 7.14, which is going to be a 7.1. Well, I can write it to put a small place there. So this is 7.14, and here I'm getting 14.3. So simplest ratio, remember this is a ratio, so we express it with 2 dots, okay, in between. So simplest ratio simplest ratio. So the simplest ratio here is going to be 7.14 over the smallest, which is 7.14, and then 14.3 over 7.14. So we are getting 14.3 divided by 7.14. I'm getting a 2.00280112, which now rounds off to an integer. So this simplest ratio is now going to be a 1 to 2. Okay, so we can go and write the empirical formula. So the empirical formula is going to be carbon 1, we don't write 1. Okay, then hydrogen, hydrogen 2. So this is what we have obtained. Hydrogen 2, CH2. So let us cross now to part C. C is here, dear viewers. We are supposed to determine the molecular formula of Z. But we already stated at the preamble that molecular formula, can somebody read for us the formula? Is equal to, empirical, yes, empirical formula, brackets into an integer A. Very interesting. But again, we know very well that empirical formula into an integer n is the same as what we call molecular mass. Very interesting. So the empirical formula is CH2, okay, into an integer n, which is equivalent to molecular mass. But the molecular mass of Z was given. The examiner is talking about molecular mass as 56. So we come and bring it here, 56. Then we go and get the mass of this formula mass. Okay, so this is going to be 12, okay, plus 1 times 2. Then the whole of it into n is equal to 56. So when we add, this is 12, this is 2, we shall get a 14n. So 14n is equal to 56. So we shall divide it through by 14, and then we shall have this. Some people even don't know how to make n the subject of the formula here. So 14 will cancel, and then 56 divided by 14, what do you get? Oh, people are saying 4. Good, that is the correct answer. So n is equal to 4. Thank you very much for the answer. Okay, so if n is equal to 4, this is not the conclusive answer. We need to go and get the molecular formula. So the molecular formula is now going to be, we go back to the empirical formula and then multiply it through by our value of n. So molecular formula is now going to be CH2, which was our empirical formula, then times 4, which is the same as saying C4H8. Here we multiply, we don't add, but we multiply. Okay, so after studying organic chemistry, people will even ask you to state the name of the organic compound you have formulated. For example, the name of this hydrocarbon is a butene. Oh, very interesting. So we shall call this one a butene. For people who are reading ahead, they already know where I'm getting this. We have an homologous cell of this nature, CnH2n. This is an alkene. So when n is 4, automatically the 2n will become 8. So it is an alkene. So if n is 1, okay, rather if n is 2, okay, if n was 2, then we would get, if n is 1, then we would have got a methane, which does not exist for this hydrocarbon. We shall go into the chemistry of this. If it is, if N is, for example, 2, it would have been an ethene. Remember, this does not exist for an alkene, but it exists for what we call an alkane. We shall talk about the alkanes. If N is 3, this is a propene. And if N is equal to 4, this is a butene. If N is equal to 5, this is a pentene. So on and so forth. They are very, very interesting, hydrocarbons under this homologous series. We shall talk about it under organic chemistry. The chemistry of carbon, majorly combined with oxygen and maybe hydrogen. We shall see getting what we call organic chemistry or organic compound. So that has been our example 5. Let us cross now to another example. Dear viewers, your friends are over complaining. You're saying I'm overfeeding you. I'm giving you a number of examples, a lot of examples. For them, they understood on the first very example. So they have forced me to give you an assignment, because that's what they have requested for. Hope you are also ready for it. If you have not understood, rewind the 5 examples, you'll get to understand. Allow me to read for you what I've written on the board, since most of you are not familiar with my handwriting. So number 1, 2.50 grams of an oxide M was reduced by hydrogen to 1.98 grams of metal. Okay. So part A, calculate the number of moles of atoms of Roman number 1, M, in the oxide. And then the atomic mass of M has been given as 64. Then Roman number 2, oxygen in the oxide. Part B, determine the molecular formula of oxide of M. Good. Then number 2, a compound Y, molecular mass 284, consists of 43.7% phosphorus and 56.3 oxygen by mass. Okay. Part A, calculate the empirical formula of Y. Part B, determine the molecular formula of Y. Part C, write the name of Y. Very interesting question. Then, number 3, a compound A, capital A, contains 52.94% X, and the rest being Y, capital Y. Calculate the empirical formula of capital A. So this is your exercise. Once you finish, you can email it on our email address, that is wakata22@gmail.com, or you can go and send it on my personal email, that is teacherswrite@gmail.com. Okay, so you can watch more examples of this on our YouTube channel, that is Wakata Online Study Classes. Wakata Online Study Classes. So immediately after a break, I'm coming with another interesting concept, and this is calculations involving the number of moles of water of crystallization. So we're going to talk about water of crystallization, how to calculate those particular number of moles. Hydrated substances is our next topic or subtopic. So immediately after break, wait for that. I'm live again. Okay, dear viewers, we'll be back from that break. So we have now, the break has taken us to calculations involving moles of water of crystallization. You can write a Z, okay, if at all the English you speak is from America, or you can write S if it is from Britain. So I'll be using all of them. So definition, we are saying that water of crystallization, we saw this under our concept of water and atmosphere. We defined water of crystallization, but I've repeated it for you here. And I'm saying that water of crystallization is the fixed amount of water which some substances do combine with when forming crystals from their aqueous solution. For example, a substance like sodium carbonate, decahydrate, okay, when it is forming those white crystals of sodium carbonate decahydrate, it combines, the sodium carbonate combines with some molecules of water of crystallization. Let us just go and get an example, the very first example. We shall not just talk about it, let us see it on the board. Example 1. Okay, so our example 1 is here about calculations involving moles of water of crystallization. We want to go and see how do we get the formula of the different, compound involving the crystals. So when sodium carbonate crystals, the examiner has given you the formula of the sodium carbonate crystals. That is sodium carbonate point X water. This is regarded to be the water of crystallization. And these are the number of molecules of those water of crystallization. So when sodium carbonate crystals were heated strongly, there was a loss in mass of 62.9, which means all the 62.9% was in water, was hidden in water. So when it was heated and the water now steamed off, then what remained with was sodium carbonate. Okay, the pure solid now remained. Good. So what is the formula of the crystals? So formula of the crystals, you can pass via the empirical formula calculation to get the formula of the crystals. But here, we need to know, first of all, what is the percentage of the pure sodium carbonate which remain. And this calls for an equation. We need to give an equation for the loss of water. Which process you should be knowing? Is it the liquescence? Is it hygroscopy? Is it efflorescence? Go back and read atmosphere. Water and atmosphere. So let us go and tell the examiner, Mr. Examiner sir, good enough, you have given us the formula of the crystals. So it is sodium carbonate, okay, point X water, which was heated such that the water steamed off to get sodium carbonate, then plus X molecules of water. So that is the water, X molecules, very interesting. Now, can we go and determine the mass, the composition by mass of the sodium carbonate? This one, because we already have this. The examiner has given you this. Remember, this is a solid which you are going to remain with, and this one now can remain as a gas which will liquefy. These are solids also. We can put the state symbols. So these state symbols are supposed to be put here at the same level. Okay, so this is a solid, then plus this is a gas. You will indicate it there. Because a chemical equation is not true unless if it is balanced and also if at all the state symbols are indicated. So let us look at the percentage composition. Percentage composition by mass of sodium carbonate only, the pure crystal, is now going to be the whole 100 subtract off the percentage of the water which was lost. Hope that is very, very clear. So this will give you a 62.9. Okay, so when you subtract, what do you get? Try to subtract 100 minus 62.9. What do you get? Oh, people are telling me 37.1 exactly. So this is 37.1%. Very interesting. Now, can we proceed and get the molar mass? Molar mass of sodium carbonate is going to be sodium, which we know that it is 23. This was supposed to be given by the examiner. We can give it here to make the question complete. That sodium is equal to 23, carbon is 12, and oxygen is 16. This was supposed to be given by the examiner, the different relative atomic mass. So the molar mass is going to be 23 times 2, okay? Then plus 12, okay? Then plus 16 times 3, okay? So when you calculate, you are going to get a 46 plus a 12 plus a 48, So this gives you a 60 plus 46, which is 106 grams. We can also obtain the molar mass for water, because now we are not going to talk in terms of elements. We are going to talk in terms of compounds. This compound, the number of moles of the compound, number of moles of water as a compound. Okay, it has changed. People should pay attention. This has changed the rhythm of now getting a particular formula. Let us go and see. Molar mass. Molar mass of water. Molar mass of water, this is 1 times 2, then plus 16, which gives us which value? 18 grams. So we shall go to our elementary method of listing now the compounds present. This time round, they are not elements but compounds. Then we talk about their percentage composition, number of moles, mole ratio, simplest ratio, and then finally up to when we calculate the correct formula. Okay, so in the ratio, from the ratio, that's when we shall determine the value of A, the value of X. So we go and say, Mr. Examiner Sir, compounds present. Compounds present, they are no longer elements. Here we have sodium carbonate, which is a compound, and then we have water. This is water. Okay, so then percentage composition. Why is it percentage composition? By mass, automatically. Percentage composition by mass. So by mass of sodium carbonate, we calculated it at 37.1. Then for water, the percentage composition was given as 62.9. So this is 62.9%. Then number of moles. So the number of moles are going to be calculated by getting the composition by mass over the relative molar mass. Over the molar mass or the formula mass. So the molar mass for sodium carbonate is 106. So this is 106 grams. And then here the molar mass for water is 18. So we can go and borrow a calculator and then try to simplify. So 37.1 divided through by 106. What do you get? And this will take us to molar ratio. So molar ratio. Okay, we are getting 0.35 to, don't forget the symbols for ratio. So 62.9 divided through by 18. What do you get? I'm getting 3.5. So I'm getting a 3.45. For 9, which is a 3.50. Okay, so we can go and think about the simplest ratio. Simplest ratio. So dear viewers, what is the simplest ratio here? Simplest ratio by dividing through by the smallest. So 0.35 over 0.35 to 3.50 over 0.35. Okay, so when we divide, we shall get a 1 here. This is 1, 2, and here we shall get a 10. I don't know whether that marker is clear enough. Can people see my 10? This is a 10. This is a 10. This is a 1. Okay, so this is very clear that the value of X, because these are number of molecules, they are no longer number of atoms. Okay, but number of molecules now of water. Different atoms, they form molecules. So X stands for the number of molecules of water, which now was lost from sodium carbonate hydrated compound. So in this kind of arrangement, we shall say that the value of x, what does the examiner need? The examiner needs the formula of the crystals. So it implies that x is equal to 10. So this implies that x is equal to 10. So therefore, formula of the compound or of the crystals, formula of crystals is sodium carbonate 0.10 water. So we pronounce this as a sodium carbonate decahydrate. Deca means 10. Hydrated means with water. Sodium carbonate decahydrate. Can everybody say that? Sodium carbonate decahydrate. Or you can just read it as sodium carbonate 0.10 water. So immediately after the break, we are coming back with another supplement as far as examples are concerned. Get a clear posture and try to keep this work into your books. I've given you a clear posture already. It is now your time to pause. For those who are watching me as a recorded teacher, record this into your books. See you in example 2.